All right, guys, Mr. Antonucci here, and we are in our third video here, solve differential equations involving inhibited growth and decay. So these are the situations where um, the amount y either grows with a boundary or decays with a boundary. So in many situations, there is an upper or lower amount, we'll call it m, that the value of y cannot exceed. Okay, so if we have an inhibited growth model, this is where there is a maximum amount of growth. The differential equation is dy dt equals k times capital M minus y, where y is less than m, and m and k are both constants. The derivative dy dt is also going to be positive because uh, k is positive and y always has to be less than m. So this factor is also going to be positive. Also, since y is less than m, that guarantees that the amount will never be greater than m. And if you actually take the second derivative, you would end up with negative k times dy dt, which would be less than zero because dy dt is always positive and you have negative k and k is positive, so it'd be less than zero. The graph's going to be concave down, and here we have a picture of that, where the horizontal asymptote would be the maximum amount. If you have a decay model, similar things going on, but it's always going to be decreasing and it's the second derivative is always going to be positive in that case. So one of the applications that comes out of this is Newton's law of cooling, where du dt equals k times u of t minus t. And in this particular situation, u of t represents the temperature of the object. Capital T represents a constant temperature. Usually that's like the temperature in the room or in the oven or in the freezer or whatever it is of the surrounding medium, if you will. And K is a constant that depends on the object. So we can actually go through and we're going to solve this differential equation for the particular solution here. So this is a separable differential equation. So we can start off by having du over u minus t equals k times dt. And we integrate both of those. This is going to be natural log absolute value of u minus t equals kt plus c. Okay, to find the initial condition c, note that t equals 0 implies that u of 0 equals the initial temperature. So we'll call that u of 0. Okay, so I would have natural log absolute value of u minus u of 0, or minus t, put the u of 0 there, equals k times 0 plus c. So c equals natural log absolute value u of 0 minus capital T. All right, so if we take this expression and plug it in for c in our general solution, then we're going to have natural log absolute value u minus capital T equals kt plus natural log absolute value u 0 minus t. Okay. I can subtract the natural log on the right side to the left side and have natural log absolute value minus t minus natural log absolute value u naught minus t equals kt. Get some more space going here. And then since we have subtraction of logs, I can rewrite this as natural log absolute value u minus t over u naught minus t equals kt. And then at this step, we're going to exponentiate both sides, and the e and the natural log cancel. So you would have u minus t over u naught minus t equals e to the kt. And in this situation, since t is less than u naught and t is less than u, we can take the absolute values off because it's not going to end up being negative. Okay. And then multiply both sides by the u naught minus t. So you have u minus t equals u naught minus t e to the kt. Okay. And then if I solve for u equals um, t plus u naught minus t times e to the kt, like this. This set of parentheses right here is very important. Sometimes the t's added in front, and then sometimes it's added behind, as you may see that. Okay, so let's do this with an example here. An object heated to 90 degrees and allowed to cool in a room with a constant temperature of 20 degrees. After 10 minutes, the temperature is 60. What will the temperature be after 20 minutes? All right, so we can start here with du dt equals k times u of t minus 20. Okay, because the constant temperature is 20 degrees. All right. Separable differential equations. So du equals u of t minus 20, or divided by that rather, equals k dt. Then we integrate both sides. And since we proved what the formula is before, we can go straight to the answer of natural log u of t minus 20 equals kt plus c. Now, at this step, I can plug in the information, okay? When the initial temperature was 90 degrees, so u of 0 is 90 degrees. So this would be 90 minus 20 equals k times 0 plus c. So natural log of 70 equals c. Okay, now that just gives us the value of c for our situation. So then we can rewrite our equation, natural log absolute value of u of t minus 20 minus natural log of 70 equals kt. Okay, so I put the natural log of 70 in for c and then subtracted that constant to the other side. Since this is subtraction, I can write this natural log absolute value of u of t minus 20 over 70 equals kt. And if I exponentiate both sides, I would have u of t minus 20 over 70 equals e to the kt. Okay. Multiplying that by 70 and adding 20 to both sides, here's what you'd have. You'd have u of t equals 70 e to the kt. So that's multiplying the 70 off, and then adding the 20 to the other side cancels that. Now, this is our equation without the value of k, but they did give us additional information that after 10 minutes, the object is at 60 degrees. So what that means is that u of 10 equals 60. So I'm going to solve that right here. So 60 equals 70 e to the 10k plus 20. All right, so I'm going to subtract 20 and divide by the 70. So you'd have 40 over 70 equals e to the 10k. And then natural log both sides. The natural log and e cancel. So you have natural log of 4/7. Actually, I'm just going to reduce that, equals 10k. So k equals natural log of 4/7 divided by 10. Okay. So we can write this as 0.1 natural log of 4/7. All right, again, that's not our final answer. That's just the value of k. So they wanted us to get the temperature at 20 minutes. So U of 20 is equal to 70 e to the kt. So K is um, 0.1 natural log of 4/7 times 20, so times T, plus the 20. Now, if you dump that into Desmos, you should get approximately 42.857 degrees Celsius. So after 20 minutes, the temperature of the object is 42.857 degrees. All right, guys, that's it for this one. Hope that was helpful to you. Take care.